In this mini-lecture, we'll apply what we learned about electron orbitals and the periodic table in the last mini-lecture to constructing energy level diagrams and electron configurations for atoms and ions. As we saw in the last mini-lecture, the periodic table is organized based on where electrons are located in electron orbitals, with each element occurring in a position associated with the orbital of the last electron added to that element. As noted previously, the progression through the types of orbitals is based on the energy level shells, or N values, which match the period or row in the periodic table for the S and P orbitals. As we progress through the energy level shells, we continue to add a new type of orbital subshell to each shell, with the first energy level containing only an S subshell to complete the shell, the second energy level containing an S subshell and a P subshell to complete the shell, the third energy level containing an S subshell, a P subshell, and a D subshell to complete the shell, and finally the fourth energy level containing an S subshell, a P subshell, a D subshell, and an F subshell to complete the shell. After the fourth energy level, the S, P, D, and F subshells followed the same pattern. However, we also noted previously that the D and F subshells do not appear at the expected locations in the periodic table, with the 3D orbitals appearing in the fourth row instead of in the third row where they may have been expected, and the 4F orbitals appearing in the sixth row instead of in the fourth row where they might have been expected. The reason for this has to do with the relative energy of each of the subshells, as these subshells in the periodic table appear in order of increasing energy. To explain this, we'll start with an energy level diagram like we saw in the third mini-lecture, which shows increasing energy levels as steps or rungs on a ladder. Remember that the increase in energy for each energy level is primarily due to the increased distance from the nucleus for that shell. Except this time, instead of using just one line to indicate the energy level, we break it up into one line for each orbital for that energy level shell or subshell. So here we can again see that there is only an S orbital for the first energy level, an S and 3p orbitals for the second energy level, and an S, 3p's, and 5d's for the third energy level. And we could continue on with the fourth energy level and beyond, with the higher energy levels including the 7f orbitals in addition to the s, p, and d orbitals. Note that this energy level diagram represents hydrogen with only one electron, and that the orbital subshells with the same energy level, or N value, are drawn with the same energy. So the 2p orbitals shown here have the same energy as the 2s orbital. And we say that these orbitals are degenerate, meaning they have all the same energy. Same thing would be true for the third energy level here. The 3s, 3p, and 3d would all be degenerate. Also note that each of the horizontal lines represents one orbital, which can have two electrons. And electrons can be filled into the diagram with an up harpoon or a down harpoon. More on this a little later. For hydrogen, its one and only electron goes into the 1s orbital in the ground state. But these higher level orbitals that we've drawn here would be possible places that the electron could go if it was excited to a higher energy level. This ground state configuration for hydrogen can also be represented with an orbital diagram, as shown on the right here, with boxes used for each orbital instead of lines, and we only usually show the boxes that actually contain electrons. This box is labeled 1s for the one electron in hydrogen, which occurs in the 1s orbital in the ground state. And finally, a third way to represent this is with an electron configuration, which is a written version of the diagram indicated for hydrogen as 1s1, where the subscript on the orbital label indicates the number of electrons in that orbital. Now, for multi-electron atoms, having more than one electron means the electrons themselves repel against each other due to their like charges, which causes a destabilization in energy, meaning their energy increases. And this causes differences in the energies of the individual orbital subshells. The energy level diagram changes slightly, and we now see that subshells of the same energy level are no longer degenerate, but orbitals within the same subshell are still degenerate. So the 2p orbitals are all still the same energy, even though the 2s and the 2p are at different energies. Generally, the energy of the subshells increases within an energy level as we go from s to p to d to f, with the s orbital for the energy level setting the starting point. Note how this leads to a curious situation where the 3d orbitals actually fall in between the energy of the 4s and 4p orbitals, which is why we see the order in the periodic table as 4s, 3d, and then 4p. Something similar will happen for each set of d orbitals at each energy level. They will always appear in between the energy of the s and p orbitals of the next energy level. And something similar also happens with the f orbitals. Note again the orbital diagram for helium still contains just one box labeled 1s, but now with two electrons, one indicated by an upward harpoon and the other indicated by a downward harpoon. And that the electron configuration for He, or for helium, is now written with a 2 subscript on the 1s orbital to indicate that there are now 2 electrons in the 1s. The electronic structure indicated by this second energy level diagram on the right will follow the same order for all elements with more than one electron. So basically everything but hydrogen and cations with only one total electron. But how do we explain this order of the energy within the subshell structure? Again, it all comes down to the electrons themselves. The energy of an orbital depends on the electron's distance from the nucleus, and in multielectron atoms, it depends on the number of other electrons present in the atom. This is because electrons are stabilized in energy, so they have lower energies, when attracted to the positively charged protons in the nucleus. So the closer they are to the nucleus, the more attraction they feel and the lower their energy. But the farther away they are from the nucleus, the less attraction they feel and the higher their energy. In multi-electron atoms, this attraction to the nucleus is further complicated by the fact that there are now repulsive forces at play between the electrons themselves, which destabilize the electron's energy, sending it higher, and because electrons that are closer to the nucleus will actually shield the positive charge of the nucleus from the outer electrons that are farther away. You can think of this as though the outer electrons are trying to look through a screen of negative charge generated by the inner electrons. So they can't see or feel the positive charge of the nucleus as it is diluted by this screen of negative charge. The attraction that an electron feels for the nucleus is referred to as the effective nuclear charge felt by the electron, and it decreases as we go to higher energy levels, where there are more inner electrons shielding the outer electrons. A lower effective nuclear charge also means that the outer electrons aren't held as tightly to the nucleus and are therefore more likely to be further away from the nucleus, which is also why we see orbitals at higher energy levels so much further from the nucleus. However, one way that electrons overcome the shielding effect is by penetrating into the region where the inner electrons are located and getting closer to the nucleus, thereby increasing the effective nuclear charge. Penetration also explains why the subshells within an energy level are at different energies. But how or why would this penetration occur? Here we see the probability distribution for the 1s, 2s, and 2p orbitals. Note that the 2p orbital actually has a higher probability of being found closer to the nucleus than the 2s orbital if we compare their maxima in the probability distribution. So this would suggest that the 2p should actually be lower in energy than the 2s, which is not what we're seeing in the diagram. The ability of the 2s to penetrate has a substantial effect on the relative energies of these two orbitals. Remember how the 2s orbital has some small probability of having an electron in the same space as the 1s orbital? This small increase in probability closer to the nucleus allows the 2p electrons to penetrate the inner shell electrons and spend a little time closer to the nucleus than they normally would, which stabilizes the energy of the 2s compared to the 2p orbital, which does not have the ability to penetrate closer to the nucleus. So, if the 1s orbital is occupied, the 2s orbital has a chance to actually feel that positive attraction to the nucleus because it can penetrate, whereas the 2p orbital would be left almost completely shielded from the nucleus because it can't penetrate. Here we see the same trend with the third energy level. By order of their maxima in the probability distribution, we'd expect the 3d to be lower than the 3p, which would be lower than the 3s, because they increase in distance from the nucleus. But instead, the penetration of the 3s and the 3p stabilizes these orbitals so much that we actually see the 3s lower in energy than the 3p, which is lower in energy than the 3d. Penetration can also explain why the 4s orbital is lower in energy than the 3d. Even though the 4s electrons are normally located much further from the nucleus than the 3d electrons, the 4s electrons can penetrate all the way into the region of the first energy level, significantly reducing the shielding effect and increasing the effective nuclear charge. So the 4s ends up lower in energy than the 3d orbitals because the 3ds do not have this ability to penetrate. So, how do we remember this order for the energies of the different orbitals? Well, my first recommendation is to get really comfortable with this diagram of the periodic table, as it can help you remember the order as you work your way from left to right across each row as you work your way down the table. But another tactic that some students use is this diagram shown here on the right, where you list the orbitals at each energy level and then use diagonal arrows to indicate the order, looping back to the start of each new arrow as you work your way down through the chart. Either way, you'll want to know the order of the orbitals for constructing energy level diagrams, orbital diagrams, and electron configurations, and I've got a few more tips for constructing these. The first step is usually to determine the total number of electrons for the element. If it is a neutral element, this will be equal to the number of protons in the atom, or the atomic number from the periodic table. If it is an ion, you will need to either add or subtract electrons from the total found in the neutral atom based on the charge that you have for the ion. When filling orbitals for the ground state, we start with the lowest energy orbitals first, so filling in the order that we've been discussing for these subshells using either the diagram on the right or the periodic table itself for guidance. This rule is referred to as the off-bow principle. Next, we remember that each orbital can hold 2 electrons each, and the Pauli exclusion principle states that these electrons must have opposite spins, which is why we use an upward harpoon and a downward harpoon to indicate the spin of the electron. More on this in the next mini lecture. Finally, in situations like the P, D, and F subshells where there is more than one orbital of the same energy, Hund's rule states that we should keep electrons unpaired as much as possible. So one spin-up electron will go into each orbital at the same energy within a subshell first, and then if there are more electrons, they will begin to pair within the subshell. So, if we start building up the electron configurations and orbital diagrams for the second row elements, we see how these rules are applied. Note for carbon that we place 1 electron into each of the 2p orbital boxes instead of pairing them right off the bat. Note for oxygen that the 4th p electron is the first to be paired in a 2p orbital, and that by the time we get to neon, all the electrons are paired. When we move on to bonding in the next chapter, it will be important to be able to distinguish between the core electrons and what we call valence electrons, as valence electrons are the electrons involved in bonding. Note that the core electrons are always part of a completed energy level shell, and that valence electrons come from the energy level shell that is not completely filled. The electron configuration for the core electrons will match the electron configuration for a noble gas, as all noble gases represent configurations where all the energy level shells are completely filled. Finally, note that there are a couple of exceptions that occur for chromium and copper within the D block due to the unexpected stability of full subshells and half-full subshells. I point this out because you might encounter chromium or copper on the homework, but I will never test on these odd exceptions as they are really the focus of different higher level chemistry courses. However, I will point out on this slide that the complete electron configuration is given for each of these elements, as well as a shorthand notation called the noble gas configuration, where the noble gas with the same electron configuration as the core electrons is noted by the noble gas in square brackets with the valence electrons given after. This highlights the valence electrons for that atom. This concludes the 5th mini lecture for Chapter 4. Please note any questions you may have about this material and how it is utilized to solve problems in the sapling homework or end of chapter exercises for this chapter. Please post any urgent questions on Piazza. I will also take questions on this material during one of our virtual class meetings, and during that time we will focus more on problem solving for concepts in this chapter.